Hi everyone, I'm Roger Benson. I'm a tutor in Earth Sciences at St Edmund Hall, and I'm also in the Earth Sciences department as a paleontologist. So I teach courses related to paleontology, field geology, and sedimentary geology.
Hi everyone, I'm Erin Saupe. I'm a tutorial fellow at St Hugh's College, and I'm in the faculty of the Department of Earth Sciences at Oxford. I'm also a paleontologist, and I also teach courses on evolution, invertebrate paleontology, quantitative paleobiology, and sedimentology.
So today, Erin and I are going to show you a demonstration interview with one of our current students to give you an idea of what online interviews in Earth Sciences are like. Before that, I'm just going to explain what happens in Earth Sciences interviews and what we're looking for when you apply to study Earth Sciences at Oxford. So for Earth Sciences, we don't set any admissions tests, so you don't have to sit an exam before coming to interview. We also don't set you any pre-interview reading or similar. So you come into the interview really with a sort of fresh mind, and we're looking to evaluate you based on how you respond to our questions. And really, our main goal is to get to the bottom of how you think and how you respond to new challenges. So it's really okay if you don't know the answers to questions right away, because we want to see how you tackle new challenges and how you apply yourself to questions.
And on that note, what we're looking for specifically, so students are selected on the basis of some key things that are outlined on our website. So those are reasoning ability, mathematical ability and potential, independence of creative thought. So are you able to sort of think laterally and generate hypotheses? Your capacity to absorb information and use new ideas to apply it to perhaps unfamiliar situations. Your spirit of inquiry, so meaning how excited are you about learning new information and about the earth sciences. Your ability to observe the natural world, so are you accurate and critical about your observations? And then your appreciation for field-based laboratory and theoretical nature of earth sciences. So do you like the multidisciplinary nature of the earth sciences where you are able to get into the field, do fun experiments in the laboratory, as well as think more theoretically and quantitatively?
Yeah, that's right. And while you're applying, you've probably had some thoughts about why you want to apply to an Earth Sciences degree rather than a different science degree, such as physics or chemistry. It's likely that you'll be asked that type of question in an interview, just so that we have an understanding of your motivation for studying this specific course rather than any other. So in our process, students have 2 interviews. So all of our shortlisted applicants have 2 interviews with tutors representing probably 3 or 4 different colleges. And that's to ensure you're seen by representatives of as many different colleges as possible. And in fact, when you apply to Earth Sciences in Oxford, we don't know which college you apply to. Our process is college blind. So all candidates are evaluated on an equal footing regardless of which college they apply to.
Hi, Jamie. Nice to meet you. I'm Erin Saupe. I'm a tutorial fellow at St Hugh's College, and I'm a faculty member here in the Department of Earth Sciences at the University of Oxford, and I'm a paleontologist.
Hi, Jamie. I'm Roger Benson, and I'm a tutor at St Edmund Hall. I'm also a paleontologist in the department. So we'll both interview you today. Thank you for coming, and thank you for your time. I guess the first thing to do is to say how the interview will proceed. So we'll ask you some questions. We'll start with some more general questions, and then we'll get into some questions that are designed to explore how you think scientifically. The main thing to say about those questions is not to be too anxious about them and not to worry too much about getting the right answers straight away. Our main goal is just to see how you think about problems. So we want you to do really well. So if it's possible, try to enjoy the process and feel free to tell us what you're thinking, even if you're not sure that it's quite right, and we'll help to sort of guide you through the process and see how you approach the questions that we give you.
Yeah, absolutely. It's about thinking out loud so that we can get a sense of your thought process. So the first question we want to ask you is, why Oxford, and why do you want to study earth sciences in particular here at Oxford?
Yeah, so What I particularly liked about the Earth Sciences course here is that it stays more broad than at other universities. So I kind of like the idea of, so I think in the first 2 years at least, you take all of the courses at the same time. And I just like the idea of getting a really broad basis for the knowledge before like specializing too early.
That's
Yeah,
great.
great. And why are you interested in earth sciences in particular?
Yeah, so it's just kind of always been an area I'm interested in. Like stuff like volcanoes and earthquakes are just kind of naturally cool. But I mean, weather stuff has just been what I've always been interested in and has just been interested in how those systems work.
Right.
Right? All right, so I'm going to ask you the first question, and it's thinking about how climate change may affect our Earth systems. As you know, climate is changing, it's getting warmer, and there are many effects of that warming on Earth systems, including the melting of ice. So there's a lot of ice on Antarctica, and let's say we're interested in estimating how much sea level would rise if we melt all of the ice on Antarctica and dump it into the oceans. So we want to melt all the ice. Well, we don't want to melt all the ice, but we want to estimate if all the ice melted and we dumped it into the oceans, how much would sea level increase? But let's say that the only pieces of information we have are 4 pieces of information: the volume of ice, the density of water, the density of ice, and then the surface area of the oceans. So what I'd like you to do is think about how you might approach this problem to roughly estimate how much sea level would rise if you only have those 4 pieces of information. So I'm going to go to Miro right now and write down those pieces of information that we have, and we can abbreviate them as well. So let's make this a bit bigger. Density of ice is dice, and then surface area of the oceans. So these are our 4 pieces of information that we have. Can you start to think about how we might roughly estimate that increase in sea level using only these pieces of information?
Okay, and can I write on the board?
Yeah, absolutely.
All right, so I'll start off with the ones that I can kind of know a bit more. So density of water is just, I think, 1,000 kilograms per meter cube. It's like slightly under, but
Yeah,
that will be about right.
that's exactly right. But actually, we're not going to use any numbers here. So you don't actually need to know that value of the density of water, although that is right. So what I want you to do is actually just use these abbreviations and think about how you would estimate that value, but not actually get a number at this point in time.
So how would I estimate the density of water using other values?
How would you estimate the increase in sea level, so that height increase, using only these 4 pieces of information? So we don't want the actual values. We don't care about that. We're just pretending like we have these actual values here with abbreviations. Yeah.
So the way I'm thinking of it now is the change in height. So I will write. So change in height.
Yep.
Would be equal to. So it will be to do with the surface area.
Yep.
Yeah. So let me just think of how it's related. Sorry.
No, that's right.
We like people to think. It's fine.
Yeah, it'll be the volume divided by the surface area. So the volume of water divided by the surface area of the oceans.
Right. Yep. No, that's exactly right.
And to get the volume of water, we would multiply the volume of ice.
So Jamie, why don't you just write down, so that's exactly right. So why don't you just write down the volume of H2O divided by the surface area of the oceans? Because that's right, that's what we want to ultimately get at, is that change, right?
Sorry for the handwriting. This is a bit different.
No problem at all. It's no problem.
It's difficult to write on Miro.
You haven't seen our handwriting yet.
There we go. So should I keep them going?
Right.
Keep going, please do.
All right. So to get at the volume of H2O, that's going to be equal to, it's going to be related to the volume of ice. And that's going to be just multiplied by a coefficient related to the density of water and the density of ice. Let me just think about what goes on top of what though.
Yeah, great. So we know that the volume of water is related to the volume of ice, but we need to think about how it is related and how we can take the pieces of information that we have, like the density of water and the density of ice, to get that volume of water.
Yeah, this is just something that should be pretty easy. I can't remember exactly how it works. I just need to think it through. So
Sure.
if I'm saying that the density of water is higher than the density of ice, so let me just write this down.
So,
Sorry.
oh no, go ahead. Go ahead.
Okay, so I'm just trying to remember which way to write down. I think it's water on top, but I just want to make sure.
So let's.
Oh yeah, go on.
Oh, go ahead. Sorry, I don't mean to interrupt you.
I'm just trying to. So if I'm going to say the volume of water is going to be less than the volume of ice, and I know that the density of water is less than the density of ice. Okay, yeah, it's got to be density of water on top.
What's the property that you're trying to conserve?
Okay.
Volume isn't conserved and the densities are different, but what is conserved that you're thinking about?
What is conserved?
Yeah.
So how do we relate density and volume?
Mass?
Yeah.
Yeah, mass is conserved, exactly. So what is density?
The mass per volume.
Mass per volume, exactly. So if we were to just very systematically walk through the pieces of information that we do have, so we have the, first of all, we start off with ice on Antarctica, right? So we have the volume of ice, we have the density of ice. So what can we get from that?
We can calculate the mass of the ice.
We can calculate the mass of the ice, exactly.
So if mass is conserved, you've said, why don't you start by writing out an equation that says that the mass is conserved?
Okay, so okay, yeah. So the mass of total ice.
Great.
So mice.
Yeah.
Oops, sorry, top is equal to. Actually, let's do this differently.
Okay.
No problem.
So mice start at the start of melting plus mass water at the start. But hopefully this can all be fit on the thing. Will be equal to let me just move across.
Yeah, that's great.
That's an equation I can use.
That's great. So you've got mass of ice at the start plus mass of water at the start equals mass of ice at the end plus mass of water at the end. But let's make the simplifying assumption that we melt all the ice, so
Yep.
mass of ice at the end is 0, and that we started with no water, or we're just subtracting. Yeah, there you go.
There you go.
Great.
That's great. So we know that the mass of ice at the start is going to equal the mass of water at the end. So then, since we can substitute the mass of ice for the mass of water, what do we need to do? We just need to get the mass of ice, right?
Yeah.
And that's a piece of information we don't have here. So how would we get that?
Okay, so to get the mass of the ice, so we have the volume of ice and we have the density of ice. So mass is just volume divided by the density. Sorry, multiplied.
Right.
Very
There
nice.
you go. Very nice. Excellent. So why don't we write that out? So mice.
So mice is equal to, let's keep on looking at the names. Vice.
Yep.
Mice, vice.
By
Dice.
Exactly. There you go.
Very nice.
Very, very nice indeed. All right. So now we have the mass of ice, and you just said that equals the mass of water. So now what can we do?
Let's write this down.
Perfect. Yep. And that's great that you're writing things down to help us.
And we can, and we can relate the mass of the water to the change in height.
How do we do?
So the volume at least.
Yep.
Yeah. So earlier you were trying to get an expression that related the volume of water to the volume of ice.
Yeah.
So why don't you use what you've got so far to change your equation that does the equivalencies of the masses into one that uses volumes and densities instead.
Okay, so to get, at some point I switched from using H2O to water. Okay, I'll keep on with water now. So this will be equal to M water over E water, density of water.
Perfect. Yeah. Great.
Which are both known at this point.
Yep. You do know. Yep.
And then once we have the volume, and then volume of water is also equal to its surface area, which would be A oceans. At some point I also switch from oceans to water. That's okay.
That's fine.
Multiplied by the height of that water. And this is now known. This was given at the start, so just rearrange. And that should be okay.
That's it. So now you have just used the information and how we understand density to be related to mass and volume to get that change in height. So to get how much we think sea level will increase if we melt all of the ice on Antarctica and dump it into the oceans. Obviously, this is a really rough calculation, and there's a lot of assumptions that we made when we did this calculation. But if we were to make these sorts of assumptions and put in some real numbers, we would get approximately about 75 meters, which is quite a lot. So we certainly don't want sea level to rise that much. But what are some of the assumptions that we made in this analysis?
So firstly, we assume that the ocean is a box, basically. Well, not a box, but we assume that it doesn't increase its surface area with radius of the Earth.
Absolutely, yeah. And what happens as we start to melt the ice on Antarctica? What happens to the surface area?
It will increase.
It'll increase, right? And what will that do then to our estimate for how much sea level will rise?
It will decrease it.
It will decrease it. Absolutely, yeah. And so if we wanted to get a more precise estimate of that sea level rise, can you think of a mathematical tool or method that we can employ that would perhaps get us a better estimate? If something's changing over time, what might we do?
You'd have to integrate it.
Yeah, I think you'd have to integrate it as well. Yep, exactly. What other assumptions did we make?
Well, we assume this is the only factor, but we're just saying this is the height based on the Antarctic. I guess we're assuming this is a kind of average density of the ice, because there's going to be a lot of packing of the ice around.
Sure, absolutely. Yeah, so the density of the ice could change, especially we know with ice sheets, there's a lot of pressure at the lower, at the base of ice sheets, which really pack down that ice, absolutely. And that will affect our estimates.
We're also assuming like the temperature of the water, like thermal expansion stuff.
Yeah, so what happens with the temperature of the water? So when the temperature increases, what happens to the volume of the water?
So if it's taking all this like cold ice water, it's going to be decreasing in temperature, and thermal expansion is going to decrease, so not rise by as much as predicted.
Right, but let's say then also as well, you have this increase in global temperatures, which is causing the melting, and that might be warming the oceans sort of elsewhere. So then what would happen to the oceans in that sense?
So that will just cause an expansion and an increase in height as well.
Right, exactly. So we would have to balance those two. And actually, it's thought that the warming that's occurring is actually going to cause quite an increase in sea level, even without any of the melting of glaciers. Great. Thank you so much. I'll pass you on to Roger.
Thanks a lot, Jamie. So we have time for another question. So sort of refresh your brain. And we're just going to go slightly lower down on the whiteboard. So I'm just going to start writing underneath the last one. This is an entirely different question. So can you see, oh, just a second, let me get this straight. Right, so can you see the line that I'm drawing?
I can see it after you finish drawing only. Yeah, there it is.
Thinner line than I expected. Let me just try and increase the thickness. Okay, let me try again.
Okay.
Oh, don't worry about that. Okay, great. So I've drawn a vertical line, and these are axes of a graph. Now, we're used to thinking about graphs that have values on their x-axis and y-axis. That's a sort of conventional graph, and we'd call those Cartesian coordinates. But this is quite a different type of graph we're going to draw. So this is a traditional graph that you're probably very used to, but I'm just going to draw to the side of that a different graph. And in this graph, we have a point in the center still called the origin. And the way we plot points onto this graph is we just have one linear axis that I'm drawing now. Can you see that?
Yep.
And that's called the r-axis.
Mm-hmm.
So one of our values is this thing called r, which describes the distance from the origin. And then the second axis is an angular axis. So it describes how far around from the vertical line that I've drawn in degrees, how far around we go. And that angular axis is called theta. So for this graph, in order to plot a point, I need two values. One is r, the distance from the origin, and the second is theta, the angle around that we go in terms of our distance on the origin. Have you come across anything like this before, Jamie?
Yeah, I came across this slightly in the end of last year.
Okay. And do you know what this is called? You don't have to know. I'm just trying to see how.
This would be polar coordinates.
Yeah, these are polar coordinates. So to get some idea of your understanding of polar coordinates, I'd like you to just plot for me what the line would look like, which satisfies the equation r equals theta.
Okay, so there it is. All right.
Yeah. So what will happen? What will happen to r as we increase theta, for example? That's a useful way to start thinking about it.
Right. So if they're both 0, it will pass through the origin.
Great.
As it increases, you won't be able to see it as I'm drawing. I'll draw this in a different color. Okay.
Well, go ahead. Yeah, if you can figure that out, but it's fine to draw it however you like.
Let's go blue. As it increases in r, it will also increase in the clockwise direction as theta by. I guess it doesn't really matter what the scale is on this.
Yeah.
So let me just think. It'll be linear. So it'll be.
It's useful to think about some other points. So let's say, like, where will the point fall when theta equals like 90 degrees?
So let's say this is 90 units away. Yeah.
Great. And how about when theta is 180 and so on?
I've now realized this is too close.
You can always the easiest thing might be to just change the position of that point. Yeah.
There.
Okay.
Scroll down. That's about double.
Yeah, great.
About a triple. Be around here.
Yeah, great.
And this is a bit far away now.
Yeah, that's fine. And then draw the line that you think, what the line would look like connecting those points.
So we'll start to spiral.
Yeah, that's great. It describes a spiral.
This is really hard to draw on this tablet.
That's all right. I mean, the main thing is that you know that it's a spiral. And what will happen as we continue increasing even beyond the line that you've drawn so far?
Yeah, it'll be like concentric.
Yeah, it'll continue spiraling concentrically. Just give me a second because I need to plug my computer in. Otherwise, we'll have a problem. Okay, great. All right. So how would a line that satisfies this equation differ from the one that you've drawn? R equals theta over 2. How would that look?
Okay, so doing the same thing again, just imagining points. Let's do red this time.
Okay.
I'll draw within the fortune cookie looking thing. Actually, I'll label this first.
You can just describe verbally what you think it's going to look like compared to the other one, if you like.
Okay. Well, I think it's better. I think I can get that right if I draw.
Okay.
It will just be, each point will be twice as close.
Yeah, okay. So that looks like a tighter spiral.
Yeah.
Okay, right. Now something slightly different to that. I'm just going to share an image with you. So I'm going to share my screen on Teams now. I can do that. Okay, can you see the image clearly that I'm sharing with you?
Mm-hmm.
Okay, I mean, what can you see in the image? We'll start just by looking at these two.
It's a couple of spiral shells.
Yeah, okay. And yeah, these are fossil shells. Do you know, have you come across fossils like this before? It doesn't matter too much whether you have or not. It's just useful to discuss what they are.
Yeah, I've seen these before. These ammonites? Or
yeah, these are ammonites. And they're extinct sea creatures that lived at the time of the dinosaurs. And these are just the shells of these animals. What's the difference if you were going to write an equation using r and theta in polar coordinates? How would the one on the right differ from the one on the left?
So it's a much looser spiral than the one on the left. So the coefficient on the theta would be larger than the one on the left.
Okay, so this has a larger coefficient multiplying with theta. Okay, and then I've got a third one down here. How does that third one, how would you change the way you draw the graph for the third one?
Let me think.
Yeah. I mean, it's useful to start with your observations. What appears different about this one compared to the others?
Yeah, so... sorry, it's quite zoomed in. It's hard to see, but it doesn't actually start at a point. It's got like a little circle inside the middle, doesn't it? Or does it still spiral in? It's hard to tell.
How big does this appear on your screen at the moment? Can you?
Maybe like 6 centimeters.
Okay.
Not got a very big screen.
Sorry about that. Let me see if I can put it on the mirror board instead. So you can probably see that. It's probably currently very small, but you can probably zoom into it more easily.
Nice.
Okay, does it appear larger now?
Yes.
Okay, that's great. Sorry for that hiccup. Yeah, so you should be able to zoom in on that as well now. If you, yeah, how does the lower one appear different to the others?
I think that possibly, maybe it's increasing at a slower rate. Or like, wait, no.
Yeah, you could take it that it's spiraling out at a slower rate. What's your observation that leads you to that conclusion?
Well, I can see that from the fact that the outer most kind of bit of the shell, I don't know what it's called,
That's fine.
is relatively thinner than the other ones. I don't know the scale, but comparatively to the center, it's smaller than the outer shells of the other ones, even though it's gone through more spirals.
Yeah, exactly. It's gone through more spirals and it's about the same distance out.
Mhm.
So there are two ways you could do it. We don't know the sizes of these things. We only know the sizes of the image. One way is it could be a tighter spiral, potentially. The other way is you could just allow the line to go around more times. So there are two ways we could vary that. Okay, I'm just entering another image now. You should be able to see, and I'm going to make it a bit bigger. Okay, so the left-hand image is one of the ammonites, and this time it's drawn rather than a photograph. And the key thing is we can also see what it looks like side on. So it was spiraling around in the plane. The image to the right of it is just a snail shell. And I want you to suggest what's different about that snail shell and how you, if you were going to add another axis to the graph, how you might capture the way that the snail shell is coiling differently to the ammonite shells.
In the first section, so the top section, they both look pretty similar.
That's right.
So they're both kind of, at least in that plane, so the r and theta plane, they are basically essentially doing the same thing.
That's right. Good.
But as it is, if I look at the other one, the lower snail one,
Yeah.
as it is spiraling further and further, it's going further and further left in the image.
That's right. Good. Okay, so that's right. How might you modify the polar coordinates system by adding another axis in order to capture that variation?
So I guess, well, it doesn't affect the other side. So if you added another axis, you'd just say the center of the line, or the center of like the line of the shell.
Mhm.
It looks pretty linear to me, but maybe that's not right. I would guess it's linear.
Okay, that's fine. You can say that it might be linear.
So it might be linearly increasing in whatever direction you're going to call that, negative, whatever direction.
Okay, I'm just going to draw out our original axes next to that image. To select the pen tool. Okay, I'm just going to draw out our original axes. That's r. That's theta. Where would you put this other axis, and can you have a go at suggesting an equation that would result in a snail shell rather than an ammonite shell?
Okay, working it. So I guess I would obviously I'd like to put it in this direction, but that doesn't work because it kind of overlaps with this. So you'd have to put it going kind of into the page.
Yep, that's fine. Draw an axis going into the page.
It's not so bad.
It's good. And you can give that axis a name if you want, whatever name you choose.
Okay, let's call that D for depth.
Okay, great. D for depth. And then what would the equation look like? For the ammonite, it was just an equation that said like r equals theta. What do we have to do in order to capture the fact that it's also moving along the d-axis?
Yeah, so the depth is related to the I mean, well, r and theta are related, so you can say it's related to both of them.
Yeah. And what does it do as the value of r increases?
So,
what happens to d?
Yeah, it will just increase, let's say, linearly.
Yeah. Okay. So go ahead. You can just express d in terms of r or in terms of theta. It's up to you. It doesn't matter which.
You want me to write an equation or like draw the line or?
Just write an equation.
Okay, so
because we know r is related to theta, you can just express d in terms of r or in terms of theta.
so we have r is equal to theta, let's say multiplied by this work.
Yeah, it's easiest if you just try to express d in terms of one of these other variables,
Okay.
and both of them.
Yeah. We can say that d is equal to negative kr.
Yeah, that's right. Yeah, so it has some linear relationship with r, and it increases, or in this case, it increases as r decreases, or decreases as r increases. Great. All right. Thanks, Jamie. So that's everything we have time to ask you. But before we go, are there any questions you wanted to ask us about the course or any other sort of aspect of studying earth sciences or the process?
Sorry, I didn't have anyone in mind.
Okay, well, that's fine. We're not evaluating whether you have questions for us or not. It's your chance. If there was anything that the student helpers hadn't clarified or you asked in the previous interview but didn't have a chance. Okay, great. Well, that's everything then. It was really great to meet you. Thanks for your time, and it's been really interesting discussing these science questions. So.
Yeah, thank you very much. It was really nice to meet you.
Thank you.
Thanks. Bye.
Hi again, everyone. I hope you enjoyed watching the video. As you could probably see, Jamie did very well. This is because he's already a student on our course. He's already studied earth sciences for the past year. But as you could also probably see, he didn't know all of the answers, and that's okay. What really helped during the interview is that he was able to voice his thought process, and so that allowed us to coach him and help him along the way and see how he was thinking. What was really great is that he proposed ideas and directions, and he used what he knew already and applied it to those unfamiliar situations, which is one of our criteria that we use.
Yeah, that's exactly right. In an interview like that, we would be impressed that the applicant was thinking their way through problems, suggesting ideas, and calmly working through the issues. Occasionally making small mistakes, but being able to pick up with a bit of guidance and get through to the end. And really that tells us a wide range of things, including things about the applicant's mathematical capabilities and just general comfortableness with equations, but as well their sort of broad engagement with science, and especially the nature of the Earth and the earth sciences. For example, in the question about ice, having some reasonable idea of how the system works, just from a qualitative perspective in the first place.
Yeah, based on the observations that he was making when you make ice cubes, for example. So that ability to make observations about your daily life and about the world around you.
Yeah, so if we had a candidate like that at interview, it's likely we would make them an offer and that they would be a relatively strong candidate. Weaker candidates might have more difficulty proposing ideas or might be able to organize their equations and thoughts less clearly and struggle to a greater extent with the questions. Stronger candidates might work through more quickly and make connections more rapidly. But overall, that was a very strong, sensible performance. Bearing in mind this is one of our existing students who's sat a year of the course as well. It's a very commendable, solid performance.